All right, here we're going to look at the cardinality of some of these sets, intersections, unions, and complements. Making an assumption here, first of all, U is going to be my universe. I'm going to ignore my red example here with D, E, and T for a moment, and then maybe we'll come back and show how these work out in that particular example. If U is the universe, and A is a subset, a proper subset of U, and B is a proper subset of U also. So they're both inside of U, but they're not U itself. Then we can look at the number of elements of each of these, and we can say that the cardinality of A plus the cardinality of A complement should equal the cardinality of the universe, right? The number of elements in a set and the number of elements outside the set should combine to be all of the elements in the universe, okay? And of course that works the same for B as well. What's interesting is when we start getting into the intersections and unions. Intersection, we really don't know. Just offhand, there's no nice formula for the cardinality of an intersection. You just have to find the number of elements in both sets, in some way using roster notation or just somehow constructing that set. However, the cardinality of a union can be found by adding up the elements in each set and not double counting the ones that occur in both. All right, so if you think about this and this being A and B kind of, you would take all the elements in one set, all the elements in the other set, without double counting things like the 0 and the 6, just counting them once. Well, how do you account for that? Things that are in both are in the intersection, and if you just tallied up the two sets, you'd be double counting those intersection points. So really what you want to do is add them up and then remove one copy of the intersection of those intersection points so that there's only one copy present and not two. Okay, so the best way to approach this is to take the number of elements in A, add to that the number of elements in B, so that's the total, and then subtract off one copy of the union so that you only have one left, right? If you do this, you're going to have two copies of the union. You're going to have, intersection. Subtract off the intersection. You're going to have two copies of the intersection, right? The intersection occurs both in here and here, and when you add them together, you get two copies of those points. It'd be like double counting the 0 and the 6. All right, so you subtract off one copy of that, intersection, and that will give you the total number of elements in the union, okay, or the cardinality, right? And so this is very useful. In our particular case here, if I was to look at the cardinality of E union T, well, that's going to be everything in E, cardinality of E, plus the cardinality of T, minus the cardinality of their intersection, E intersect T, which in our case is cardinality of E is 1, 2, 3, 4, 5. Cardinality of T is 1, 2, 3, 4. Now there's definitely not 9 elements in this set, the union. So we have to subtract off the intersection, which is 2. Right, because the 0 and the 6 are technically double counted, so I've got to pull off a 0 and a 6, that's 2. And 5 plus 4 is 9, minus 2 is 7. So the cardinality should be 7. If I look at the number of elements in the union, 1, 2, 3, 4, 5, 6, 7. There it is. Okay, so obviously I could count it up from the Venn diagram, but if I don't have a Venn diagram, I can use the cardinalities of the original sets and the intersection to find the cardinality of the union.